Okay, folks, if you're watching this and you're in my controls class, it means you just got back from spring break. And so what I'd like to do is a review on how to tune a PD controller of a second order system. So the second order system that I'm going to do is going to be a spring mass damper system. And it's going to, the equations of motion are going to be m times x double dot plus c times x dot plus k times x equals f. And f is going to be a PD controller. So f is going to equal negative kp times x plus kd times x dot. And we're just going to assume that we have perfect sensor measurement and we're measuring that. So if we get our equations of motion into a form that we can actually work with, I'm going to divide out by m, and I'm going to move the controller f to the other side. I'm going to get x double dot plus c over m plus kd over m times x dot plus k plus kp over m times x equals 0. Okay, and so this is my essentially closed loop system here. And so if I want to, I can solve this with a bunch of different ways. So I can do the transfer function way. I can do the state space way. I can just do the normal EOMs way, which is really similar to state space, so I'm just going to leave it off. And so we're going to do these two. Now before we move on though, let's plug in all of my parameters. So I'm going to put my parameters here. I'm going to say I'm using problem 26 from chapter 4 of, let's see, if you're watching this and you're not in my controls class, this is Norman Neese control system engineering. Okay, so M in this problem is 5. Let's see, C is 2, and then K is 20. And so what I want to do first is just by looking at this problem, let's look at the. Let me move this up here. This is the closed loop system, and so let's look at the just the open loop system. So to do that, let's start with looking at the transfer function. So what would the transfer function be for my system here? And what I'm going to do is for open loop, I'm going to go ahead and set kp and kd to 0. And so my transfer function is going to be just I'm going to do the transfer function way. I'm going to just have a gain of 1 for now, and then I'm going to do, let's see, it's going to be, if we take the Laplace of both sides, we're going to get big X times s squared plus c plus kd over m times s plus k plus kp over m times, just like that, equals 0. And so you might think that x equals 0, but this Laplace transfer function assumes initial conditions are 0. And it also assumes that it's an impulse response. But I'm going to hit this thing with a step response, so that'll go away. So then my coefficients are just 1, c plus kd over m, and then k plus kp over m. And I'm actually going to call this variable the denom. And I'm going to put denom in here. And so I'm going to move this to this side and this to this side. And I'm going to go ahead and just run this. And so here's our transfer function, 1 over s squared plus 0.4 plus 4. So if you recall, if I want the step response, so I'm just going to throw in a step g here, and I'm going to run this. It's going to show me this. And if you notice, the amplitude only goes to 0.25. So first thing that I want to do is I'm going to throw a clear, a CLC, and a close all in here. And if I want this thing, rather than going to 0.25, I actually want it to go to amplitude of 1. And so I look at this and I say, all right, what I want to do is make the gain equal to the natural frequency, which the natural frequency is equal to this guy. So if I say let's look at natural frequency, and let me maximize this, and damping ratio. Omega n is equal to the square root of this guy. And so if I put omega n squared in here and I run this and I look at the plot, it turns out that this thing goes to 1, which is exactly where I was headed. So the other thing I can look at is now I can say, man, this has a lot of overshoot. But how much overshoot does it have? Well, the natural frequency is omega n. And so how do we get the damping ratio? Well, remember that when you have your characteristic equation equal to this, the general second order system of equation looks like, our transfer function looks like s squared plus 2 times z, and I'm using z because zeta is a built-in function in MATLAB, times omega n times s plus omega n squared. And so we already have omega n, so really our equation is that c plus kd over m equals 2 times z times omega n. And so if I want to solve for z, all I have to do is just say, well, that's c plus kd over m, that whole thing divided by 2 times omega n. And I'm going to go ahead and get rid of the semicolons here. And so if I run this and take a look, it looks like my natural frequency is 2 and my damping ratio is 0.1. So my damping ratio is really, really low. What would my poles be? So my poles, there's 2 ways to find this. I could come down here and I could say, well, let me grab the denominator and put it up here. I could do roots of the denom, right? That would give me my poles, and I could run this. And there are my poles, negative 0.2 plus or minus 2i. Another thing that I could do is I could say, well, I actually know what they are. It's negative z times omega n plus or minus the square root, the square root of 1 minus z squared, and then that whole thing times omega n. And so I could say, well, s1, my first root, is negative z times omega n plus omega n times the square root of 1 minus z squared. And s2 is the exact same thing except minus. And if I run that and look here, looks like I forgot to put an I in there. Let's see, I, run that one more time. And there we go. So I get the exact same thing. The other thing that you can do is not only can you do roots of denom, you can also run pzmat on G. So I'm going to move G up to here. I'm going to do pzmat of G. Here are my poles and zeros. Notice there are no zeros in this transfer function. So pzmap of G, I'm going to throw a figure down so I can see both. And so here is my step response, and then here is my my guy here. And so let me run this one more time. Get this out of here. It should tell us some cool things. Yeah. So look at that. So my pole is negative 2 plus or minus 2i. My damping ratio is 0.1, but it actually tells me I overshoot 2, which is 72%. So let's compute that as well. So if I wanted to get poles and zeros, let's compute all of the things that matter. So let's do overshoot. So overshoot is going to be OS exp of negative z times pi over the square root of 1 minus z squared. All of that times 100, so I should get 72 for that, and I get 72.9, which is exactly what I want. And then let's see, my settling time is t settling is 4 divided by z times omega n. And so my settling time is 20 seconds, and so if you look at the plot here, you can see that it takes a long time for these oscillations to settle out. My rise time, there's no closed form solution for that, so we'll skip that one. But you can get peak time, but peak time is not really important. In my opinion, overshoot and settling time are the most important. Okay. So let's tune our PD controller now. So this is all of our open loop stuff. So I don't really like the settling time and the overshoot of this system. So the idea is let's add feedback and get the system to a way that I like. So I'm pulling from the book, and I'm saying I want the settling time to be 15%. Oh, sorry, the overshoot to be 15% and the settling time to be 0.7 seconds. So I want overshoot to equal 15% and settling time to be 0.7. So that's completely different than what I had before. So let's backtrack and figure out what we want here. So from overshoot, you can get the damping ratio. And so I'm going to pause this and derive this really quick here and and then I'll come back and show you what it is. Okay, I'm back. So that was quite a derivation. So I copied this piece of code here, which is the how to compute overshoot, and I divided by 100, and then I natural logged both sides and multiplied by the square root of 1 minus z squared. So I get this equation here. And then I squared both sides, and then I factored out the terms on the left, and then I brought the z squareds to one side, divided it out, and then square rooted the whole thing. And so the damping ratio as a function of overshoot is here. And so what I've done is I've set the overshoot closed loop to 15. I've computed the damping ratio based on that overshoot, and then I've recomputed it just to make sure that I got the overshoot that I wanted, and I did. So here's my overshoot that I wanted. My damping ratio is 0.5, and my closed loop transfer function, my closed looped overshoot is going to be 15%. And so now that I have my z, I know that settling time is 4 divided by z times omega n. And so what I can say is I can say that z times omega n times settling time equals 4. And so omega n equals 4 divided by z times settling time. And so omega n is going to be, and I guess I could have left the z there. I'm not entirely sure why I did that. But anyway, so omega n will be 4 divided by z times settling time closed loop. And I said that settling time closed loop was 0.7. Okay, and if I run that, looks like my natural frequency is 57, which is huge compared to my natural frequency of 2. Okay, so now that I have my natural frequency and my settling time, I can actually make a transfer function from this, right? My transfer function is s squared plus 2 times z times omega n plus omega n squared. So I can go ahead and make g closed loop equals transfer function, and this is going to be omega n closed loop. Actually, you know what, let me just go through here and call this CL. That makes that easier. And let's do Z CL, and oh shoot, I'm going to have to do this for all of these. I just don't like typing this much. Oh, I forgot to put ZCL in there. I wonder if that's actually... Okay, so omega n is only 11. Okay, that's not that bad. No big deal. Okay, so transfer function omega n squared, and then 1. Let's do denom again. Denom closed loop 1, 2 times z closed loop times omega n closed loop squared. Let's throw in roots of denom. Let's do s1 is negative z closed loop times omega n plus square root I times omega n closed loop. Oh, and I forgot closed loop here. Times square root 1 minus z closed loop squared. That's the roots, and then the other one, s2 closed loop. That's going to give me those ones. I'm going to do denom of this one. I'm going to drop a figure down. I'm going to do a step response of g. I'm going to do a PZ map of g. Closed loop, and I wrote out the whole thing. Why did I do that? Closed loop, and I'm going to do PZ map of closed loop. And let's see, it looks like I got some errors, or, oh, I didn't throw a figure down, of course. Okay, so let's see. Oh, and I didn't do omega n squared closed loop here. I didn't do denom closed loop. Okay. Okay, I figured it out. I keep forgetting to put this underscore CL for all of these. Anyway, so let's look at this. So I've got, let's see, my transfer function open loop is s squared 0.4 plus 4. My transfer function closed loop is 122. Wow, it's significantly ramped up. 11.43, 122. If we look at, here are my closed loop poles. Here are my open loop poles. So here they are closed loop negative 0.2 plus or minus 2. And then here they are closed loop negative 5 point whatever, 5.7 it looks like. Oh, I can read it here. Yeah, here's the output of roots, and here's the actual computation of the roots. Negative 5.7 plus or minus 9. And then the biggest kicker is this guy versus my closed loop system. And this looks way better. I mean, this takes 20 seconds to settle. This only takes 0.7 seconds to settle, and there's only 15% overshoot. So what exactly is KP and KD, though, right? Let's see if we can compute that. So what would that be? What we would have to do is go in and go back to our equations. So omega n closed loop squared equals k plus kp over m. So that means if I just square, I'm sorry, that's actually what it is. So if I just multiply this by m, that gets rid of this. And then if I just subtract k, that would give me kp. So kp equals m times omega n closed loop squared minus k. And let's see what it is. So k is, oh gosh, 590. So in a real system, I doubt we can do a kp of 590. But you know what? This is a simulation, and we can do whatever we want. Okay, so then how do I get kd? So this is a determination of kp. And then we've got determination of kd. So kd, how do we get that? Well, we have 2 times z closed loop times omega n closed loop equals c plus kd over m. So if I just multiply by m and then subtract c, that would give me kd. So kd is m times 2 times z closed loop times omega n closed loop minus c. And so kd is 55, which is, seems reasonable. The thing is, there's no units for this, okay? So I have finished tuning my PD controller, okay? And at the end of the day, you know, this is my, wrong figure. This is my closed loop step response. Now, what if I wanted to do this using state space? So let's do that. To do that, we need to put this thing in first order form. So remember, I've got my, let's just take the open loop transfer function, or the open loop equation of motion, which is this one here. I'm going to copy this one and put it down here. And so first thing we got to do is we're going to divide out the m over m over m over m. And then we say that x vec is x and x dot, which means that x vec dot is x dot x double dot, and then that's going to be an A matrix, which is going to be 0, 1, and then negative c over m, sorry, negative k over m, and then negative c over m times x and then x dot plus 0 and then 1 over m times f. And so there's my state space form. So my A matrix is this guy here, copy, and then my B matrix is this guy here, copy, boom. And so I can run this, and there's my A and B matrices. And so what's neat, remember about state space, is if you want to get the poles of a state space, you just do the eigenvalues of A. And so there are my open loop eigenvalues, which are my poles. And if we scroll up, these are the same as, where did they go? What just happened? There we go. I don't know what happened. There it is, right there. This is the same as the ones that I saw up there. Okay. So now let's simulate this. So I'm gonna take. I'm gonna have to make this a function. So I'm gonna get rid of the clear. I'm gonna make this function PD controller tuning. And then I'm going to come down here and I'm going to actually put all of this into a, I'm going to comment out, well, yeah, I'm going to comment out EIG. I'll just leave it there. So I'm going to do, I'm going to put a function in here, dxdt equals derivatives of t comma x. And remember, this is a vector, so I'm going to say that now I just need to copy a and b. And I'm going to just go ahead and make K, M, and C globals. I'm also going to make KP and KD globals. Or I'm going to leave those off for now. So let's go up here and let's make globals for K, M, and C. Mass spring damper system. And I'm going to let F equal omega n squared. And omega n squared is somewhere up here. Here it is, square root of k plus kp over m. And then dx dt, and here let me just make this like the same, that way it's not ridiculous. X vec dot. So I'm going to say x vec dot is a times x vec plus b times f, just like that. And now I just do my OD45, t out, x out, equals OD45 at derivatives. I do what, the t-span, so 0 to 20 seconds, and the initial conditions. And then I can plot, let's throw a figure down, and I'm going to plot t out, comma, x out all, comma 1, and that's probably going to throw me an error, but it'll be, I guess it'll be okay. Undefined variable, oh, kp is undefined, of course. So I'm going to set kp equal to 0 right now, artificially, just because. Of course, I had to multiply this by m. When I got the plot here, it didn't go to 1, and I'm not entirely. And the reason why it didn't go to 1 is because my gain was wrong. My transfer function up here has omega n squared in the numerator. And that's because the last term here is k plus kp over m. But my B matrix has 1 over m here. And so I forgot, in the transfer function, I forgot to throw that in there. So I don't think that's going to throw off my kp and my kd. At least I hope not. So if I multiply by m there, we should get, yeah, there we go. There's my open loop system response using state space. And here's my open loop step response using the transfer function method, and they look identical. This one goes to 30 and this one goes to 20, so they're a little bit different. Okay, so so let's try to add feedback. So let's add feedback. And so I'm going to say, instead of f equals that, I'm going to say f equals kp times x, vec of 1, and then kd. And are these minuses? I already forgot. Did I say minus? I did, yes. You know, I'm just going to copy this so I don't mess anything up. Put a here, and then x is x vec of 1, and x dot. And you know what? Let's do this the fancy way. So I'm actually going to do k times x vec like this, and k is negative kp negative kd, right? If you multiply that out, you get what you want. And I might need to throw in an m in here if I need to, but we'll see. So let's see what happens. Let's see. It looks like it might not have liked it. Why does it always do that? It's freaking me out. Let's see. Oh, KP and KD are undefined. So let's go ahead and put KP and KD in here as globals. So we got to add KP and KD in here as well. So let's run that. And ooh, no, that looks terrible. Let's see, what am I missing here? Is it the fact that, is it because there's no step input? I feel like we still need m times omega n squared in here. So this is the feedback component here, but we still need to add the step response. And I feel like in order to get this thing to go to 1, oh no, it actually worked out pretty well. But it looks like it's completely different than what we had before. So let's see what's going on. Okay, well, the issue is that I have KP equals 0 here. So even though I have KP and KD as globals, if I set KP to equal 0 here, it's going to completely mess up the whole thing. So let's see, my closed loop transfer function only simulates for 1.2 seconds. So I only need, instead of simulating for 20 seconds, I only need to simulate for 1.2. And there is my state space solution, and here is my my transfer function method. So it worked. We got it. I'm sure there'll be a million questions. One other thing that we can do is, what if we wanted to find the poles of the closed loop state space? So remember, that's EIG of A tilde, or A closed loop, say. And so what is A closed loop? Well, that's, if you remember the state space equation, you have x vec dot plus equals A times x dot plus B times F. Well, if F equals B times, x vec, if B equals K times x vec, well then A closed loop is just going to be A plus BK. And so I could just do A closed loop as A plus, and then I have B times K. Well, what's K? Well, I can come down here and grab K and throw it up here, and I can run this, and my closed loop, boom, there it is. My eigenvalues of my closed loop system are the exact same thing that I computed way up top here. And so, I mean, here's my A matrix, here's my A closed loop oh shoot, it doesn't work because these are all global variables. I mean, sorry, these are all, this is in a function now, so I'm gonna have to get rid of this. So there's my closed looped A matrix. If you notice, these bottom two terms are completely different. You also notice these two terms here are the same as the closed loop transfer function characteristic equation down here. So everything's connected. Hopefully this was enlightening. And basically, for those of you who are just watching this video for fun, post some questions in the comments. For those of you in my controls class, head over to Sakai and you can read about your assignment that has to do with basically doing the same thing I did using MATLAB. So email me if you have any questions, and I will try to respond as soon as I can. So let's just do a little refresher. We have our mass spring damper equation of motion. We're using PD control, so we're having proportional gain and derivative gain. Here's my closed loop equation of motion. Here are my parameters. For open loop, I'm going to set Kp and Kd to 0. I compute my natural frequency and my damping ratio. Here are my closed loop or my open loop poles. Here are the coefficients of my denominator of my transfer function. I can also get the poles using the roots function. Here is my transfer function with omega n squared as the gain, so that the last term is the same as the gain. And then I do PZ map to get my poles, which should be the same as the roots, which should be the same as this equation here. I compute my open loop overshoot and settling time using the equations in the book. I look at the time response via step. And then I say, with feedback, I want overshoot and settling time to be 15 and 0.7. So I rearrange the equations to get my closed loop settling time. I then use my closed loop, my closed loop damping ratio. I use the closed loop settling time to get my natural frequency of my closed loop system. And then I get my closed loop denominator, my closed loop poles, my roots. The poles computed using the negative zeta omega n equation. I have my closed loop transfer function. I use the step response to see what it looks like. I look at the closed loop poles using PZ map. And then I use these equations to compute Kp and Kd based on that. And then finally, I make my A and B matrices. So I take my transfer function and my equation of motion, convert it to state space. I can compute my poles using the EIG function. I can also compute my closed loop poles using K and A closed loop, which is just A plus BK. And then I simulate using OD45, and here's my system here. So I have my A matrix, my B matrix, my natural frequency here used to scale the forcing function, my feedback gain matrix, my PD controller here, and then just my step. This is the step response part of it, and then the equation x dot equals ax plus bu, and in this case u is f. And I'll show you all the plots one more time. So here's the closed loop step response from state space. Here's the closed loop poles. Here's the closed loop step response using transfer function. Here's the open loop step response using transfer function. And here is the open loop poles using the transfer function. Alright, I hope you enjoyed this video, and I will see you some other time.